you need to know. It is also, when you are filling out brackets, like our Final Four brackets, you're weighing like what's the probability of this team winning over something else. So when we talk about probability, the important things that we know is probability is, it can be written as a fraction, it can be written as a decimal, and it can be written as a percent. It's always between 0 and 1, okay? No chance that it would happen at all, okay? 1 is 100% chance that it will happen, okay? 100% chance that if you bring in an apple pie, I will eat it, okay? No chance whatsoever that I will eat mushrooms, okay? So then we have this space in between, and they will be numbers. So you could have 1/4, 1/2, 3/4. So here we would have a 0.25 or a 25% chance. 1/2 would be 0.5 or 50%. 3/4, 0.75 or 75% chance. Okay? So as you are answering and figuring out your solutions, they will all be within 0 and 1. You will not get something outside of that. Okay? So when we talk about probability, typically we're wanting to have that outcome that we're talking about it. So as we talk about probability, we will be assuming that the thing we are looking for is happening. So we are looking for the positive outcome. So if I'm saying the probability of rolling this die and getting a 6 means all of the positive times that I actually get a 6 out of all the others. So probability, when we look at it, it is written, we write it as we write through a question that we're asking, and we're saying the amount of something out of some total. Okay? So there's two things that you're always going to need to know whenever you come up with probability. The number one is the total. Total of what? Well, total of whatever we're looking at. And then we've got an amount of. So we talked about that some with the permutations and the combinations. We needed to know the total that we were starting with and then how many we are taking. So this is the same thing for probability. We're always going to be looking at a positive amount out of something else. So we'll keep using that terminology as we're writing through. There are two different types of probability. One is theoretical and one is experimental. Theoretical is what should actually happen in best case scenario. So when we talk about theories, you know, this is perfect situation. Everything's always going to happen according to like all the perfect odds. And then experimental is reality. So it's your reality check. So if I said I have 5 tokens of every color in here. Okay? So I'm going to have 5 people just randomly pick one. Pick one. Okay. So there's 5 of every color in here. So if I had 5 people pick, there's a 1 out of 5 chance that someone got a blue. Did anyone get a blue? Did anyone get a blue? No. So my experimental of what actually happened, you can just pass the tokens down, move them a little bit, didn't line up with what technically should have happened. Okay, so there's a difference. We can see that there's a difference. You know, I think especially whenever we look at the Final Four bracket, the probability of all number ones losing When's the last time that a number 1 didn't make it in?
It never happened.
I don't think it did.
History was made.
You know, and so when we look at the theoretical probability was that at least one of them is going to make it to the finals, right? The experimental, what's actually happened means that there's not a single perfect bracket in the United States right now, right? Okay, so when it comes to probability, how do we write it? What do we need to know? Probability is written with a P, okay? So it kind of looks like permutations, except we're going to give some instructions next to it. So it has a parentheses and then it will have something written there. It could be a phrase, a sentence, a number, a color, whatever. But the event that is inside the parentheses is the event that you want to happen. Remember, with probability, we are looking for a positive outcome. So we're saying the probability of this event happening is going to be that event happening. So your actual event happening over all of the total outcomes that could possibly happen. Sometimes we know the total outcomes. Sometimes we have to use our permutations or our combinations to actually find the total outcomes. So that was why we had to use our counting method, use our permutations, use our combinations beforehand so that we can get this bottom part. Okay? So with a good portion of it is we're going to look at the wording of a question. So let's consider this one. You have a 6-sided die. I have a die here. 6 sides on it. Numbered 1 through 6. Are any of the sides duplicated? No. Okay? So if I roll this, what is my probability of rolling a 4? 1 out of 6. So we would write that, the probability of 4, because this is what I actually want to happen. And we're going to say, what are the total outcomes that we could get on a 6-sided die? 1, 2, 3, 4, 5, or 6, right? So we have 6 total outcomes. How many of these outcomes, how many ways can I actually roll a 4? There's only one way to roll a 4. So the probability of rolling a 4 is 1 out of 6. Okay? For the colored tokens that we had, I have 5 colors. I'm going to have 4 colors. 1, 2, 3, 4. 4 colors. 4 colors. 5 of each of them. Okay? So, how many total tokens do I have in that bag? 20. I have 20 tokens. How many of them are blue? 5 of them were blue. Okay? So my theoretical probability was 1 out of 4 would be a blue. We had 5 people pull and no one got a blue. So we had a difference there. Okay? So as we look through, we're just going to be answering that question, what do I actually want to happen and how many ways can that event happen? So let's look at B. What is the probability of rolling an odd number? So on a die, what are my numbers that I can roll? So I would say probability of odd, it would be written like this. Probability of rolling an odd number would be, I could roll a 1, 3, or a 5. Okay? So how many ways can this be positive? Can it be, I got what I wanted?
3 ways.
3 different ways. How many total ways?
6.
6. So it's 1/2. Okay? So let's look at C. What is the probability of rolling a number less than 7?
100%.
100%. Because how many ways could I make that true? I could roll a 1, 2, 3, 4, 5, or 6. Correct? Out of 6 ways. So I would have 6 over 6, which would be 100. So we could write this probability 1/2. We could write it 0.5. We could write it 50%. All of these are acceptable answers. Right? need those? Okay. So, with a die, it says you will always be told, like if you have a question, they'll either say a 6-sided die or a 12-sided die or a 10-sided die. They're going to tell you what you have, and that's your total amount. So that's your bottom number that they give you. Okay? So what happens when we have something where we don't know the total amount? So let's look at this one. You put a CD that has 8 songs in your CD player, and you set it to play them at random. Okay? The player plays all 8 songs, so it's using up all of them, right? So what is the probability that the songs are played in the same order that are listed on the CD? So when we look at it, probability of order listed. So as we work through our probability, what are the top is the ways to make this true? How many ways can the songs be played where they're in the order listed on the CD? One. There's only one way. So we're asking how to make this true. So then out of the total ways that they can be played, what do we have? We have 8 songs. If we use our fundamental counting method, we would say that how many options do we have for the first song? 8, and then,
7, 6.
so we're going to work our way down. Okay, so this looks like something, because they're being played in a certain order. Is that a permutation or a combination? Permutation. So we could say we need a permutation of 8 things taken 8 at a time. Correct? Because we're playing all of them. And that will give us our bottom number. Okay? Permutation of 8 things taken 8 at a time is just our 8 factorial, which is 40,320. So our probability of being played in the order listed is 1 out of 40,320. Okay?
Yeah, we should just do that for the rest of the class.
Just keep listening to songs. There you go. Okay? So what if we have those same 8 songs? We have our same CD. And now, keep our probability up, it says you have 4 favorites on a CD. So half of the songs are your favorite. Okay? What is the probability that 2 of them are played first in any order? So now we have shrunk our probability. We're going to look at it, and it's our 2 favorites. I wrote are played first. So we're looking at just these 2 songs. The rest of it doesn't matter. Right? We're only looking at the first 2 songs in the list. And so that means our total is now not the first 2 out of 8, but we're looking for our favorites out of the first ones. We've shrunk what we've wanted to find. So we're going to ask ourselves, as I have up there, 2 of our favorites first out of any way that the first 2 songs could be played. So according to our fundamental counting method, how many options do we have for our first song?
Well, 4. Yeah, 4 options.
Out of all ways, I'm playing the entire CD.
Okay.
I have 8, and then what do I have for the next one? 7. So there are 56 ways that we can play our first 2 songs. Correct? Could I also write that because it can be in any order. So if it's in any order, we're looking at a combination instead of a permutation. Combination of 8 songs taken 2 at a time. Okay. Which would give us 8 factorial over 6 factorial, 2 factorial. So when we have 56, this is wrong. Because they say any order, that means I've got duplicates. Right? When we have duplicates, we have to divide it out. So we have 56 divided by 2. Gives us 28. Okay? So we get the same thing if we did our combination. So now what about the top? 2 of our favorites first. So what is that going to look like? Does the order matter?
No.
No. So we have a combination. How many songs are we looking at? We're looking at only our favorites. So I have 4 favorites. How many of those favorites am I wanting to take? 2 of them. If we used our counting method, we would say I had 4 options for the first song, 3 options for the second song. That gives me 12, but there's a duplicate, so I really only had 6. Right, this would be 4 factorial over 2 factorial, 2 factorial, writing out our combinations. Okay. So 6 divided by 28. They both have a 2 in common, right? So 3 out of 14. What's the odds? What did it come out to? 3 divided by 4. 0.21? 21%? 1/5? It's a pretty good chance.
It is half.
1/5? No, it's a fifth of it.
Well, it's half of your favorite songs are like half the CD, so.
Yeah, so it raised your odds.
Decent chance, yeah.
It raised your odds than it did on the other one. Okay. So let's look at another example. Okay. A spinner has equal size sectors numbered 1 to 8. So are any of the numbers duplicated?
No.
Nope. Right? So what is the probability of spinning a 6? How many positive ways are there to get a 6? There's only one way, is to actually land on a 6. How many total ways, total options do we have if we spin? 8. So the probability of spinning a 6 would be 1 way out of 8 different ways. Right? 1/8. Okay? So what would be the probability of spinning a number greater than 5? We're going to rearrange that and put greater than 5. So how many ways are there to make this true? What numbers could we choose?
6, 7,
6, 7, or 8?
Oh, greater than
So there are 3 ways to make that true out of 8 total ways, total different options that it could land on. So the probability of spinning a number greater than 5 is 3 out of 8.
37%.
37%. 1/3. A little bit more than that. Any questions on how to write these out? Is this making sense? Okay, hopefully it's pretty easy. Okay, so we have 9 students. I've got 9 students in my class. They're all on the math team because they're all so brilliant. Okay, and we draw their names in order to decide who's going to go. It says, what is the probability that 3 of the 5 seniors on the team will be chosen last? I changed that then. It should just be chosen in any order. Okay, so it's kind of like in here. I've got 8 students in here. I have one senior, right? Are you the only senior one?
So.
Okay. Oh, yeah, I forgot. Aaron's also senior. So we've got 2 seniors. So the probability of me choosing 2 seniors out of this class would be 2 out of 8 if I had to get it. Okay? So let's look at this. We're looking at them in any order. So when we see this word in any order, we immediately know we're looking at a combination. Correct? So the probability of me choosing a senior out of anyone, so at the top we're looking at our positive ways that we can choose a senior. We're asking for 3 of the 5 seniors. So I've written a combination of 5 seniors taken 3 at a time. Does that make sense for the top one? Because I'm wanting to find 3 out of 5 seniors. So we're looking for the probability of a senior, of 3 seniors. Okay? And then out of anyone. Okay? So 9 students, I'm drawing 3 names. It says draw 3 names one by one. So I'm picking 3 options, right? Those are the 3 people who are going to compete. I've got 9 people total. So I have 9, 8, 7. B would I fill it in? It doesn't matter what order, because if I had Will, Jace, and Joshua on the team, it's the same as me having Jace, Will, and Joshua on the team. Or Joshua, Jace, and Will on the team. It's all the same people, right? So we had a combination of 9 people taken 3 at a time. Gives us our total ways that we can fill those 3 slots on a team. So then I'm finding the odds that my entire team is only seniors out of any ways that I can fill the slots. So we ended up with 10 options out of 84, which was 0.119 or 11.9%. And whenever you check your homework or if you see me work through all these slides, I will usually always try to write both of them. Either answer is acceptable, but I'll always try to write both. I want you to see that the decimal correlates to the percentage. Work. So sometimes we have to use a combination or a permutation to find the different numbers that we're looking at. Okay? So when it comes to experimental probability, why would you need to use that instead of theoretical probability? Well, sometimes you don't have theoretical probability. Sometimes you might have just had a survey and you're looking at the results of the survey. You might have data from a chart, you might have a pie chart, something that's filled out. A restaurant might be looking at sales that they've gotten over the last month. Like Wills and Catering, you might be looking at, hey, this is my consistent, these are the last 10 catering events that I did. And so instead of looking at, man, perfect case scenario, everyone's picking the same amount from the same 10 items, he might look at it and go, man, everyone's really only choosing these 6 items and we're never choosing these other items. So we've got some experimental data based upon something that we've gathered. Okay, so we can historically look at it and come up with a probability based upon the data that we have when we don't have some perfect case scenario. So in this, it says, a survey asked internet users for their ages. The results are shown in the bar graph. So are all of these the same? No, they're not the same. Which in theoretical, you would say, I picked the same number of 21-year-olds and the same number of 40-year-olds and the same number of 50-year-olds, okay? So we've got something that's different. We need that experimental data. Find the experimental probability that some randomly selected internet user is at most 20 years old, okay? So when they say at most, I've written it right here, we're looking for less than or equal to 20, okay? So when I'm looking at that category, it's going to fall in the category that says under 21. All right? So they're going to be 20 from 1 to 20. So what are the positive ways that I can make this happen according to my data?
1,636.
So there's 1636 positive ways for me to make that happen. Out of how many people are we looking at? So we're looking at total number of users because this is users under, so then I have to have total users. So the thing that we need to make sure is that what we're putting on the top is the same like unit that is the total that we're finding. So if we were to add all of these numbers up, if they ask you this, you would take 1636 plus 6617 plus 3693 plus 491 plus 6, and they're going to total add up to 12443. Right? So the probability of finding somebody under 20 is going to be 1,636 out of 12,443 people. Okay? So then it asks you for B. What about finding someone at least 41 years old? So we're going to change this and say greater than or equal to 41. Well, did my users change?
No.
No, so I can leave my users on the bottom. Now I have to find 41 and over. Do I have a category for 41 and over? Okay. I actually have 3 categories for 41 and over. So that means I've got to take all 3 categories and add them together to get the total number of people that were 41 and over, which is 4190, and that gave us a 0.337, which, how would I write this as a percent?
34%.
Yeah, 33.7% or 34% if you're asked to round up to a percent. Okay? So again, verbally, we're looking at a number out of a total number. Now, we have learned about theoretical probability and experimental probability. There's also geometric probability, because probability, since it's a ratio, can we go back and just say we're basically comparing two things? Right? It's a ratio of something compared to something else. That's what we're looking at. So we can have geometric probability, and I could compare the area of this triangle to the area of the square. Okay? I could compare the area of the circle to the area of the square, or the circle to the area of a triangle. We could compare lengths of sides. So because it's set up like a ratio, then we're allowed to have things that are comparison. And when it comes to geometric probability, you will often see this. This is a very common question that I've seen on standardized tests. Okay? They've given you a circle inside this square, and they give you the radius. Why would they give you the radius? What does the radius tell us about this entire question? What are things that we can find out?
How big the circle is, the circumference of the circle.
Okay, you could find the circumference. What do we know about the diameter?
How long it is, how wide it is, I guess.
Okay. So if my circle is circumscribed inside my square, the radius is 3. How far is it across total? 6. So what does that tell me about the side of my square?
Because it's 6.
It's also 6. Right? So what does that tell me about my area of my square?
6. It's
36.
36.
6 times 6, because each side is 6, right? So when they give us the radius, they are giving us lots of extra information. That's why they will always give you a radius, or they will give you something that has broken that radius up, so then you can find the total radius of it. Very often in your book, I don't remember if I assigned you a question on this, they do a target. Like that. And they might say that from here to here is 2, and this is 3, 3, and 3. So then you have to add up the different ones to get your radius. Right? So our radius here would be 11, which means my entire circle would be, the side of my square would be 22. So we're using those tools in our tool belt to say, what did they give me? How do I find what I'm getting? This is a very common one. Okay? So if they ask, what is the probability of hitting the circle? Okay? I need to know at the top, how many ways can I hit the circle? Right? Because we're getting the positive outcome. We're saying, I am definitely hitting the circle. What are all the ways that I can hit the circle compared to all the ways that I could hit anything? Well, hitting anything on there happens to be what shape? The square. So technically we're saying the circle, so hitting the circle compared to hitting anything. We replaced our hitting anything with hitting the square because that's all of it. Right? So we're looking at comparing area. What is the area of the circle to the area of the square? Well, we know that the area of the square is 36. We figured that out. What is the area of the circle? The circle is pi r squared. If my radius is 3, 3 squared is 9. So I have 9 pi. We're at the stage where we're not going to be multiplying this out by 3.14 a lot. Okay, we're just going to leave it as pi. So then we can reduce 9 over 36 to 1 over 4. So that can be written as pi fourths. And then if you need to find an actual percentage, this would be 3.14 divided by 4. Right? Which is 78.5%. Okay, so you got a pretty good chance, 3/4 chance of hitting the circle. Okay. So let's look at this one. This one, we have to use our brains and kind of deduce a little bit on this, okay? So you have recorded a 2-hour movie at the beginning of a DVR that has 6 hours of recording time. So let's put our 6 hours here. 3, here we go, okay? So you've recorded a movie at the beginning. So here's your movie. Agree with that? Okay. Starting at any random location on the DVR, your brother decides to record a 30-minute show. What is the probability that your brother's show accidentally records over part of your movie? That means that it's starting anywhere in this spot. Okay? So first, what are we comparing? They're asking us the probability that it actually records over. We're looking for the chances that it hits in this spot, this first spot, compared to anywhere it can record. Right? So what are all the places that it can record?
6 hours worth.
Can it record 6 hours worth?
No,
It's a 30-minute show. So it can record anywhere from 0 to 5.5. Okay? Because the end of the DVR is 6, so can it actually start recording at 6?
No.
Because it's 30 minutes, so it has to take up a portion. So the absolute latest that it could start recording is at 5 hours and 30 minutes, right? For the show to get recorded. Does that make sense? So this is one where you have to go, oh, I would have immediately put 6, but in reality, we're recording a 30-minute show. So it can go in 5.5 hours worth of space is anywhere that it can hit. Okay? Where can it go to actually record over it?
0 to 2 hours.
Anywhere in 0 to 2 hours. So the positive is if it records anywhere between 0 and 2 hours, we're going to make that positive. Remember, we are looking for the chance for this to be positive, for it to be true. Okay? So anywhere in those 2 hours out of 5.5 hours that it has to record will be the chance that it will be actually recorded over. Okay, so there's a 36.4% chance that your brother's going to record over your movie that you have on there. So when we break it down, it can take something that initially kind of looks a little complicated, and we just plug in what we know, and comes out with our ratio that we have. So my number one suggestion as you're going through your homework is don't make it more complicated than it needs to be. Okay, these should be pretty easy, not a lot of confusion. Okay, so how do we take this as we wrap up 3.1 and then apply it to other things? Well, we're going to go through some notation. I'm going to show you some notation that your book does not show you. Because it is notation that is universally used on most, it will completely used in college, if you take any college classes, math classes, and on standardized tests. So if you haven't seen it and you go, I don't know what that means, we're going to go through that, okay? So there's different ways. So the same we had, permutations means the order matters, combinations, the order didn't matter. We have all these things back and forth. We've talked before about and or, especially when we had series, we had some in permutations. And will always mean multiplication, okay? So I am doing something, so we're folding papers or whatever, like I'm doing something and Anna is doing something, we're combining what we have, that's always going to be multiplication. Or always means addition. It's what I have or it's what you have. So we're looking at those. So if you can remember that ors equal addition and equals multiplication, your That's a huge step forward. So let's go back to that one where we rolled the die and we were looking for odd numbers. And we said it was 3 out of 6. We could also say the probability of rolling a 1 or a 2, or sorry, if I'm looking at 1 or a 3 or a 5. So the probability of rolling a 1 is 1 out of 6, plus, since it's or, the probability of rolling a 3, 1 out of 6, or, just plus, probability of rolling a 5, 1 out of 6, and I end up with 3/6, 1/2, okay? So we've gotten the same answer. So ORs give us our addition, okay? OR is written as a union sign, okay? So you may see it as probability of 1 union 3, like that, with this U sign, okay? And is written as an intersection. It will be an upside down N. It always helps me remember because and has an N in it, and this one looks like an N. Okay. So these are two mathematical symbols that you will see a lot as well. So I kind of walk through and use them interchange. I want you to be very familiar with seeing those. Okay. So when in your book, as you're doing your homework, 12.4 works all with OR problems, and 12.5 works all with AND problems. So we're going to look at OR problems first, and then we're going to discuss AND problems, but we're going to go over all of them today in class. So if we were looking at the outcome of two different events, mutually exclusive is the term that you're going to hear. Mutually exclusive means that one event has no effect on the other event. Okay? So when I roll these two die, they are mutually exclusive. Whatever I roll on the green die has no effect on what I roll on the blue die. Correct? Okay. Now, if I am picking coins out of the bag, and I take a coin out, and then I return it, and I ask Joshua to take a coin out, are those mutually exclusive events? Did he start with the same coins that I started with? Yes. Put it back in. That is called with replacement. If you hear the term, if it says with replacement, you started back over at the beginning. So that means whatever I picked had no effect on what Joshua picked. Okay, so when we have with replacement, it also puts it back in a mutually exclusive category, because each time that it's pulled, it's basically starting back over the beginning. You're forgetting what happened beforehand. So when we can have events that either have nothing in common, I've done it here like they have nothing in common, they don't overlap, they share no parts. Okay? If I am looking at a probability that I pull something or Joshua pulls something, we are adding them. And it's simply the probability of each event added together. Okay? So you can see with the circles are completely separate. We're just going to add the probability of one, and so it will be written like this: the probability of your first event, which is A, plus the probability of your second event, B. And however many more events you want to have. This can be 2, or it can be into infinity. You could have 3, 4, and 5, and we would just keep adding the probability. So this is like we were saying, the probability of rolling a 1, or the probability of rolling a 3. We could keep going all the way down. Okay? Now, when you have mutually exclusive events, and then now they start sharing. Okay? So now they're not mutually exclusive. You've taken 2 separate events, but they overlap. we have an intersection. Okay? So again, we're looking at an intersection would be, we would say, this is where it's A and B. We're using and, so this is our mathematical symbol. Our intersection sign, which also has an N in it, so intersection and both have N's. So we're looking at that. Okay? If I was going to say I've got my probability of A or my probability of B, how do I combine these? We can look and see that there's a part in the middle that overlaps. Okay? If I were to add all of these up, let's look at this. If I have 4 dots in one and 3 dots in the other. Okay? I have 4 in this one and I have 3 in this one. I would say I have 7 dots. Do I have 7 dots up there? How many dots are actually on there? 6. 1, 2, 3, 4, 5, 6. So we can't just add the first one to the second one because we've counted the middle dot twice. It got counted in the first one and it got counted in the second one. So when we are looking at intersected parts here, we need to always remember that what is added in the middle here is going to be added twice. So to find our true probability, we're going to have to extract out what was added twice. Right? So I have a couple of the intersections. Union, when you hear the word union, it just means it all together. I think union we mostly hear like husband and wife, come together in one union. So it's all of the space that's taken up by all of it. Union is our U symbol, so that's just all of it. Okay, that's our or. It's yours or it's mine. It doesn't matter whose category it lies in, it's all of ours. So like if you have different rooms in your house, it's like it's your room or what's found in your sister's room, whatever it is. It's all that's encompassing. Intersection, so that's our and, is only this part in the middle where they both overlap. And you can think about the intersection of 2 roads is only the part that overlaps. It's not all of the roads. The intersection is only that section where it overlaps. Okay? So there's these 2 formulas that you'll see in your book. I'm gonna break these down. Okay? So when they're mutually exclusive, we already talked about that. We've got 2 separate circles. I've got the probability of my first circle plus the probability of my second circle, because what I am saying is I want the chance that it could fall in this one or fall in that one. Right? Okay. So since we have or, we've just added it together. Now, if I want them to fall in one circle or the other, but the circles happen to have an overlap, I have the chances that it falls in the first circle or the chances that it falls in the second circle. But as we learned with the other, we've got some overlap. So we're going to have to subtract out this middle section. And it is written as the probability of A and B, which can also be written as the probability of A intersection B. A and B. So when we're looking at actual numbers, we're going to be using these 2 formulas, but I want you to understand where they came from. So when we're looking at or, we're adding them, but we're having to subtract out that overlap. Or if they're mutually exclusive, we don't have to worry about it at all. Any questions of these 2 compound events? Compound means we're just adding more than one thing, more than one together. Now, because probability can at max be what? 1. Because it can only be 1, and because we're trying to find a positive outcome, what's the opposite of a positive outcome?
Negative outcome.
A negative outcome. So if I want things to add up to be 1, and my positive outcome is 1/2, that means my negative outcome has to be 1/2 also, right? So we always have a positive and negative, and they're going to add up to be 1. The way that is written is we have this symbol, which looks really familiar. When we were doing matrices, remember, when we're doing inverses and we talk about our inverse function, we keep using this symbol, so it's nothing new. Our inverse function is our complement. It means it's that opposite part of it. So it gets used again. It is nice when they use the same symbol and you go, oh, I've seen this before. That the complement, this also has to do with, in geometry, when you have complementary angles and they add up to a certain amount. All right, so we're using all these same terms beforehand. Okay, so the complement is written the probability. So if we have the probability of A, which is the probability of it happening, we have the probability of A with our hash means that it won't happen. And we know that happening and won't happening always have to add up to be the number 1, because we have to end up with 100%. So if it is happening, there's a part that's not happening. And all of that's going to add up to be at 100%. So we can write that as the probability of our complement is 1 minus the probability of A. We could also say that the probability of it happening plus the probability of it not happening is equal to 1. And then we can rearrange this however we want. Right? The probability of happening is 1 minus the probability of it not happening. The probability of not happening is 1 minus the probability of it happening. We're just rearranging our truth statement. That the positive plus the negative adds up to be 1. Okay? So let's look at some examples and work through logistics of this. Okay? So a card is randomly selected from a standard deck of 52 cards. I brought cards so that we can have some visuals. So I have cards here. These are all arranged. What do we know about cards?
There's 4 suits.
4 suits. What colors are they?
4 colors.
4 colors?
2
So
colors.
2 of them are red. 2 of them are black. Okay. How many cards are in each suit? 13 cards. This is important stuff to know. 13 cards in each. Okay? So that means I have 52 cards overall. So how many of them are red? Half of them are red. So 26 of them are red. 26 of them are black. Just kind of working through this. I have face cards. They only call an ace is not a face card. So we have queens, kings, and find jack. Okay, queen, kings, and jacks are face cards. So that means that I've got a queen, king, and jack of each suit. So how many face cards do we have?
12.
We have 12 face cards. Okay, because I have 3 in each suit, so 3 times 4 is 12, right? So here's some information that we know about a standard deck of cards. It says, what is the probability that it is an ace or a face? Okay, so if we were writing this out and I was going to break this up initially, I would say the probability of it being an ace plus the probability of being a face. Everyone agree? I changed my or into a plus sign. Here. Now the next question that I need to ask myself, is there any overlap between these? Can any of these cards, if I pick it, be both an ace and a face at the exact same time? I'm not talking about drawing different ones because it says you draw one card. So can this card be both an ace and a face at the exact same time?
No.
No. So that means these are mutually exclusive. They have no effect on each other. Okay? So I'm not having to subtract out any duplicates. So how many aces, if we look at the probability of an ace, we're going to ask ourselves, what are all the positive ways that I can make an ace? I've got 4 positive ways out of how many cards can I pick? Yeah, I have 52 different ways I can pick those cards. Which I could rewrite that as 1/4, right? Sorry, 1 out of 13. Not 1/4, 1 out of 13. Sorry. Okay. Now, what is the probability of having a face card? 12 out of how many cards total? 52. Okay. If we left, let's leave it since we're adding. 4 out of 52, 12 out of 52. So what is my total probability? 16 out of 52. Excellent. Okay. So let's look at a 6-sided die. Okay. If I roll a 6-sided die, I'm just going to roll one die on it. It says, what is the probability of rolling a multiple of 3 or a 5? So we're going to rewrite it how we have it initially. So we're asking ourselves a multiple of 3, which means what? 3 or 6 for that one, or a 5. Okay, so the multiple, so we've got a multiple of 3, which means we could roll a 3 or a 6 there, plus the probability of 5. So we ask ourselves, is there a way that I can roll this die once and it be both a multiple of 3 or a 5? And a 5 at the same time, okay? Because I'm looking at 3, 6, and 5. Those numbers don't have anything that overlap. So these are mutually exclusive. So we have nothing to subtract out. We have our circles. For our first one, we've got 3 or 6 in there. So that gives us 2 out of 6 ways, right? Multiple of 5 gives us 1 out of 6 ways. So we have 2 6 plus 1 6 is we've got a 50% chance. Rolling that. Okay. So with a union, when you are combining these events, you're always having to ask yourself, do I keep part of this? Okay, so we're answering those questions. Is there an overlap? So let's look at this one. A card is randomly selected from a deck. Okay, of 52 cards. What is the probability of it being a heart or a face card? Probability of being a heart or a face card. Okay? So first we ask ourselves, how many cards am I picking from when I'm picking one? What's our total? 52. Okay, so I know I'm looking at 52. Is there a chance that I could pick a heart and it be a face card? Yeah. So with one draw, I answer yes to both questions. Yes. So now we have this overlap. Okay? So we've got heart and we have face. When we write it out, we would say the probability of it being a heart or a face card. Heart or a face. Okay? And then we have some overlap. What are all of the ways that this can overlap?
King, queen, jack of hearts, so 3.
Perfect. So I have a king of hearts, a queen of hearts, and a jack of hearts are ways that I can make one draw and get both, answer yes to both of it at the exact same time. So I'm going to have to subtract out the probability that it is a heart and a face because we have to subtract out that overlap. So if I just added them together, I would have 3 cards that got counted twice. Okay? So as we write this out, we know we've got our probability of it being a heart. We used or, so we have a plus. The probability of being a face minus a set of overlaps for them. So let's look at that. Here's some logistics of it all written out. So what is the probability of being a heart? I've got 13 cards out of 52 that are hearts that will answer yes to that question. How many cards do I have that answer yes to being a face card? 12. Okay? How many of the cards answer yes to it being both a heart and a face? 3 of them. Okay? So now we simply have addition and subtraction of a fraction. So 13 plus 12 is 25. 25 minus 3.
22.
22.
Right.
Yeah, I
Yeah.
probably wrote the wrong thing up there. Yeah, 22 and then I did it. So 22 out of 52, which simplifies to 11 out of 26. So 0.423, how else would I rewrite that?
42%.
42.3%. Okay. Any questions on this overlap part? Okay. So let's look at this one. One 6-sided die is rolled. What is the probability of rolling a multiple of 3 or a multiple of 2? So let's look at what we've got here. So I'm looking at a multiple of 3 or a multiple of 2. What are all the ways that I can roll a multiple of 3?
3 and 6.
3 and 6. What are all the ways I can roll a multiple of 2?
2, 4, and 6.
2, 4, and 6. Do they share anything in common?
6 is
So is this mutually exclusive?
no.
No. Because if I'm looking at the multiple of 3, I could have a 3 and a 6. If I'm looking at 2, I can have a 2, 4, or a 6. So I've got a part that is shared. So when we write that out, we're going to write the probability of it being a multiple of 3. What do I do with my or?
Plus.
Plus the probability of it being a multiple of 6 minus the probability of it being a multiple of 3 and a multiple of 6.
Multiple 2, but yeah.
Multiple of 2. Thank you. There we go. Okay, so the probability of it being multiple of 3, how many ways can I get that?
2 ways.
2 out of 6 ways. How can I get a 2?
3 out of 6 ways.
3 out of 6 ways. And how many ways can it be both? What number does it share?
About 6, so 1.
6. So 1 out of 6 ways. So I have 5 minus 1 gives me 4. 4 6. 2/3. 0.66. 66%. Right? Okay, now, sometimes finding, like we learned last week with the permutations, sometimes what they're asking us to find involves a whole lot of probabilities. And it's a lot easier to find what we don't want than it is to find what we do want. Right? Because what do we know? What we do plus what we don't has to do what? Equal 1. So if finding what we do want is a whole lot of work, can we find what we don't want to get our answer? Yes. So let's look at this one. The probability of rolling a multiple of a number or a 5 is 4 out of 6. So if the probability of rolling a 5 is 1 out of 6, what is the probability of rolling the multiple? Okay, so we're using our things and going, what do we know, what do we not know? And then what number could it be a multiple of? Right? So they're asking us, we've got the probability of rolling some number that's a multiple of some number. Okay? Let me go back this way. Probability of rolling a multiple of a number or the probability of rolling a 5. So I'm doing these two, and it says it equals 4 6. Okay? If I know that the probability of rolling a 5 is 1/6, I'm going to replace it. What is the probability of rolling that number? How do we get here?
3, 6.
3/6. Or 1/2. Okay? So we just took our word problem and we just plugged in our numbers. Okay? So 3/6 or 1/2 is our probability of rolling the multiple of a number. Okay? So what number would it have to be to give me 3 options out of 6? 2. 2, 4, and 6. Right? So it'd have to be the multiple of 2. Okay? So let's look at this one. Last year, this is, I think, one of your homework problems. Last year, a company paid overtime. So what are we looking at? We're paying overtime or hired temp work during 9 months. Okay? Overtime was paid during 7 months. So the probability of being paid overtime is 7 out of 12 months of the year. Okay, because if they're saying last year, they're looking at a whole year. Okay. We know that says temp help was hired during 4 months. So the probability of having temporary help was 4 out of 12 months. It says, in checking the annual payroll, what is the probability that the auditor will select a month in which the company paid overtime and temp? Okay, so we're looking for this overtime and temp. Where do we have this in an equation? We know that we have the probability of our first event plus the probability of our second event minus the probability of the overlap is equal to that whole union. Okay? So they're asking us for this. What are the chances that this happened? This is the part that we're looking for. What did they tell us? How many months did they actually pay?
12 months.
They,
Well, 9 months.
9 out of 12. Okay? So all we're doing is we're taking a regular equation and we're just plugging in numbers. It's just kind of the figuring out of what numbers do I actually plug in somewhere. Okay? So we have our equation. We know what our probability of A is. It's 7 over 12. Plus our 4 over 12 is our temp minus whatever the overlap is. Right? So that's our probability of our A and B happening at the exact same time is equal to 9 out of 12 months. So now we're simply solving for an empty space. So we have 11 out of 12 on one side. So 11 minus 9 gives us 2. So we have 2 out of 12 chances that there would be an overlap. So we can use this formula to just plug in the parts. So we can find the overlap and we can find just the or section. We can solve for either part of it. That one. Okay. When we want to find that probability that's too hard initially, let's find the opposite. It says when 2 6-sided dice are tossed, there are 36 different possible outcomes. Correct? If I'm using my fundamental counting method, how many different ways can I toss the first die? 6. How many ways can I toss the second one?
6.
Okay, so I have 36 total ways. Find the probability of the sum not being 8. And I just wrote, that's a lot of probabilities to add up. Because then I would have to add up 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, and 12. Because if I rolled a 6 and a 6, 12 is the highest that my sum could be. Correct? I don't want to find all of those. So instead, let's just find the probability of the sum actually being 8. Okay? So how many ways can I actually get an 8? So if I'm looking for the probability that the sum is 8, and I've got two different die, 1, 2, 3, 4, 5, 6, 1, 2, 3, 5, 6. How many ways can it add up to 8? I could have 2 plus 6, 3 plus 5, 4 plus 4, 5 plus 3, and 6 plus 2, correct? Okay. So I have 5 different ways out of all 36 ways that I can actually make it be an 8. Did they ask me for getting to be an 8? They asked me for not being an 8. So what do we do with our 536? What do we know?
It's going to be 39, I think.
That our plus and our ways that it's not 8 has to add up to 1. Right? So I've got 36 out of 36 ways minus 5 out of 36 ways gives me 31 out of 36 ways that it's not 8. Make sense? So sometimes we can use that complement to get the other way. Right? Okay. Is there any way that we can have a mutually exclusive event and it have overlap? If they are mutually exclusive, can there ever be overlap? No, there can't be. So the probability of having a mutually exclusive event and it being overlapped is 0. They will never ever overlap, okay? So let's answer this question. What about the complement, the probability of an event and its complement? Are they mutually exclusive? So the probability of it being true and the probability of it not being true.
It's either one or the other.
It's either one or the other. So are they mutually exclusive?
Yes.
Yes, they are mutually exclusive. There will never be overlap for them. Okay? So, as we were learning about or, what about when it's and? What if you want all of it at the same time? Okay? So, there's two different ways that you can have and events. You can have and with replacement, like I talked about before, or you can have it without replacement. So again, we're looking at either, they call that dependent events or independent events. When they're independent, that falls into our mutually exclusive category. When they're dependent, there's a special way of writing that. And we write it like this. Okay? We're saying that the second event depends on what happens in the first event. So it's written B with a line and an A. Okay? Now, it is always assumed that the first event happened with a positive outcome. Remember, probability is, it's actually happening. So if we say the second event happened given, the words you will also see are given that the first event happened, or it'll be written B line A. Okay? So independent events, rolling these die, right? What I roll and what Aaron rolls doesn't matter. You take the same die, you're rolling it again. When we had the coins, when I took out one and I put it back in and then I asked Joshua to take out one, completely independent events. They are not dependent upon it. If I draw a card from my deck of cards here and I put it back and I ask Anna to come draw a card, you have the same options that I had because I put it back. We started over. So those are all independent events. Now, if they're completely independent, the same way that if they were completely mutually exclusive, all we deal with are just those two events. So just like whenever it was mutually exclusive for the or, and all we did was add them together, when they are mutually exclusive for and, all we do is multiply them together. Easy breezy. Okay, so we're going to take the probability of the first one and multiply it times the probability of the second one. Those are super easy. Okay, it can also be written with our and sign, so that's our little intersection sign. And it works for, it doesn't matter how many. So I can have every single one of you guys in here roll a die, and we're just going to multiply them all together. Because every single event is completely independent of what the person before them rolled. Okay? So let's look at this one. You serve 200 customers, you work in a pharmacy, and of those, 105 buy an over-the-counter medication. Okay? What is the probability of them buying an over-the-counter medication? So we're looking at the probability of an OTC. How do I make that true? How many people made that true?
105.
105 made it true out of how many total?
200.
200. Okay, so we're simply writing our ratio for it. Okay, so now we're going to add more events together. So now we have two independent ones. A game machine claims that 1 in every 15 people win. So our probability of winning, they're telling us, is I can make that true 1 time out of 15 total times. When we find that probability, it says, what is the probability that you win twice in a row? So we are assuming that it's positive. We're assuming that the first time there's a win, and we're assuming that the second time there's also a win. So we would have 1 out of 15 times 1 out of 15, which is a 1 out of 225 chance of twice in a row of you winning. That's why you don't gamble. Okay? So you spin a wheel. I spin a wheel, step back, Tessa comes up, she spins a wheel. Do they have anything related?
No.
Nothing at all, okay? So it says during your turn, you get to spin the wheel twice. So 2 different times that you're spinning. What is the probability that you get more than 500 on your first spin and then go bankrupt on your second spin? So again, these are completely independent events. They have this wheel. I gave you the details. The total spaces are 24. And 500, to get over 500 are all the little A marks. So we've got 1, 2, 3, 4, 5, 6, 7, 8 ways to make that positive. So we have 8 out of 24 makes you positive that you got over 500. You have 2 out of 24 that give you a bankrupt. So you have your first spin and your second spin. Gives you a probability of 1 out of 36 to have it in that order. Okay? So again, if we're going to add it, we can add to 3. So we've done 1, we've done 2, now we can do 3. It says in a survey, 9 out of 11 men and 4 out of 7 said they were satisfied with a product. If the next 3 customers are 2 women and a man, so I have my events, so the first customer is a woman, second one's a woman, the third one is a man, what is the probability that they will all be satisfied? So we're looking specifically at, for a woman to be satisfied, what did they tell us? 4 out of 7 were satisfied. So we're plugging in our numbers that make that true. 4 out of 7 were satisfied. This is another woman. So she has 4 out of 7 is satisfied. The man says 9 out of 11 were satisfied. So his was 9 out of 11 makes that true. So all we do is multiply those together to get our final probability. Okay? Now, just like with the OR, it always has to add up to 1. We have the same complement. So the chances of it happening is equal to 1 minus the chances of it not happening. Right? Same thing. Or the chance, you could say the chance of it happening plus the chance of it not happening is equal to 1. Okay? So in this case, it says it's the same survey question, but they're asking what is the probability that at least 1 is not satisfied? So that means finding the chance that 1 or 2 or 3, and I've got 4 customers, or 4 customers are not satisfied. Well, I don't want to find all of that. What if instead we found the probability that everyone is satisfied? That would be the opposite, correct? So if everyone is satisfied, we know that there was a 9 out of 11 chance of being satisfied. So we need it for all 4 guys need to answer the question, yes, I'm satisfied. That gives us this large number, which comes into 0.448. But they don't, this is if everybody is satisfied. I want the chances that at least one is not satisfied. So I'm going to subtract it from 1 and get, there's a 55.2% chance that at least one is not satisfied. Okay? So, conditional probability is whenever it is dependent upon your other outcome. Okay, we talked about that. When it's and, it is written in this form. When they're conditional. So instead of having probability of A times your probability of B when they're mutually exclusive, now we've changed our second event to be B given that A happens. That's all we've done. We've taken our original one and we've now put a condition on it. Okay? So when we put a condition, it means we have shrunk our pool. I'm going to go over a different one than this one. Okay, let's look at this one. Okay, so this table shows camp attendance for 3 age groups in 1 town. So for A, find the probability that a student attended camp. So a listed student attended camp. So we are looking at all the students that make that true. So they said yes to camp out of all of the students that were surveyed. Okay, so first, to find out how many were surveyed, we've got to add all of these numbers up, correct? So our total number of students is 478 students. How many actually went to camp? We're going to add up all the ones that went to camp, and we got 220. So to say yes to camp, we've got 220 out of 478. So 46% of all of the students said yes to camp. Now on B, it says, what is the probability that a child in the 8 to 10 age group did not attend camp? So we have now shrunk our entire thing with this guideline of saying it's only in 8 to 10-year-olds. Okay? So we are looking at no camp given that they are 8 to 10-year-olds. So are we now looking at all 478 students? No. We're only looking at 8 to 10-year-old students, which is 156. So we've put a condition on it. We've shrunk down what we have. So now only 62 did not go out of the 156. So anytime we are shrinking our pool, we're putting a conditional probability on something. Okay? So as we walk through, these are the questions that we ask. Is it independent? Does it have an overlap? Is it dependent? And then maybe are there some duplicates in there? Okay, so let's look at this one. You randomly select 2 cards from a standard 52 card deck. So we've got this, and I'm going to randomly pick 2 of them. Okay? What is the probability that the first card is not a face card and the second is a face card if you replace the first card? So when I say if I replace the first card, are these independent or dependent?
Independent.
Independent. So all we do is multiply our probabilities together. Super simple for it. Now, if I did not replace them, we would have to look at something different. Okay? So let's look at that one. The probability of drawing not a face and then a face if I do not replace. So officially the not a face was 40 out of 52 because we have 12 face cards, right? So 40 out of 52. But now we're going to write it drawing a face card given you drew not a face. So that means that you actually did draw not a face card initially. But I didn't replace it. So how many cards are left?
51.
51. So do you see how this bottom number has now changed?
Yes.
When we have a conditional probability, your totals at the bottom will not be the same. Okay? So if you are multiplying conditional probabilities and your bottom totals are the same, stop, go back, look at it again. Your totals cannot be the same on the bottom because you removed something. So now I've got all my faces are left because I'm saying I actually drew not a face card. So I can say all my faces are left, so I still have 12 of them, but now I only have 51 cards to pull from. Okay, we got 2 minutes. We can do a couple more. Okay? So you randomly select 2 cards. So we're looking, the first one is a diamond and the second one is red. If we replace the card, we're looking at completely independent events. So we can just look at diamond and we can look at red. Correct? Now, if we do not replace the first card, our first one is still a diamond, so that's 13 out of 52, or 1/4. Now in this one, picking a red, given that you picked a diamond. So first, we've changed our total to we only have 51 cards left. So then let's think about the top. How many red cards are there? Oops.
26.
26 red cards. But I already picked a diamond, so do I still have 26 red cards left? Because a diamond is a red card. So now I only have 25 cards left. So this second probability depended upon what we picked, and it changed our numbers that were placed in there. Right? That's it. That's all of it. So your homework is listed. The test is rather short. I have already posted the test, but it's not going to be due. It's not as part of your homework assignment for this week if you don't want it to be. So you can choose to do your homework and then do your test and be done with it. Next week we're starting trigonometry. Or you can do your homework. I can answer any questions next week, and then you can take your test next week. But it's on there. It's up to your discretion. All right? It's like 17 problems.